Hello, it's David Leroy here, and in this slide presentation I'm going to be talking to you about Cohens Kappa and how we calculate this and what this type of statistical measurement is indeed useful for. Lots of research, science, and in particular psychological research, relies on observations that people make about things that they're observing. The question people would have about research that relies on subjective judgments is one around the consistency of observations that are made. And the question is, how are those judgments reliable? And what measures have the researchers used to ensure that the measurements they're making are reliable? And how can they communicate to us that indeed the measurements are reliable too? And how exactly would they go about calculating some measure of inter-rater reliability? Let's think about an example to help us understand why we would need to consider inter-rater reliability. Consider a situation where researchers are interested in looking at the effectiveness of drug A versus drug B in treating cancer. And in this type of situation, people who are willing to take part in the study would be randomly assigned to one of those treatment conditions, and they would have their cancer treated using drug A, and the other group of people would have their cancer treated using drug B. The researchers want to know how effective are those drugs in treating the cancer, and to do that they have to take scans of the affected parts of those patients, look at them very carefully, and make decisions on whether the cancer tumours are at stage 1, stage 2 or stage 3 of cancer. So imagine the researchers had done just that. They're looking in this example at 10 different scans from 5 people who have been treated with drug A and 5 people who have been treated with drug B. And they've indeed gone and made ratings about whether the tumours they're looking at are at stage 1, stage 2 or stage 3. Now, eyeballing this data, you can sort of see that the numbers for drug A are larger than the numbers for drug B, indicating that patients taking drug A had their cancer proceed to a higher stage. And so from just looking at this data, we might think, you know what? I think drug B might be the best drug to treat this particular type of cancer. Now, if these researchers were to communicate that to other scientists or other practitioners that are interested in knowing this, they might be asked some questions. And one of those questions that they would be asked by people who are interested in knowing which drug is the best is, how can we rely on this data? What assurances can you give us that drug A really, in reality, is not the best drug to be treating cancer, and that drug B is the best drug? It could be just a stroke of luck or a quirk about the particular researcher that they just happen to see larger and more progressive tumours in the patients with drug A. It might also be that the researcher knows which group people are in and therefore which drug that they have been taking. And if the researcher was at all biased in any way, they might be more inclined to give drug B a slightly lower rating and subconsciously more inclined to give drug A a slightly higher rating. But anyway, this problem can be rectified if we introduce the judgments of a second researcher. And this is where we're interested in whether or not two people can independently look at the same raw data and come to similar conclusions and judgments. So the question is, are the researcher's judgments similar to an independent researcher's judgments who is looking at the same data? It's good practice to have someone code or reconfirm the observations that you want to be able to make. And that's just good science, that you can be sure of yourself and sure that whatever it is that you've discovered isn't simply an artifact of some experimental bias on your own part. So, indeed, the second research judgments are recorded on this slide. And you can see that we've put a tick or a cross beside the ones that agree with the first researcher's judgments. And so you can see the first researcher for drug A scored the tumour as being stage 2, and so did the second researcher. And you can see as you're going down the list, there's a degree of similarity between judgments. They're not all equal, but they seem to be roughly similar to what the first researcher observed. So how similar are both of these researchers' judgments? Well, one method that you can approach there is to calculate percent agreement, and this is a pretty simple and intuitive type of calculation to conduct. What we're really interested in is, well, what percentage of the time did the researchers agree? And then that would give us some measurement or indication of their inter-rater reliability, their level of agreement. So you can see there was 10 observations made by each researcher in all, so we've got an n equals 10. We have 8 agreements, so 8 times when they were looking at the slides, they made and came to the same judgment. And then if we divide 8 by the total number of observations, we get 80% agreement. And that in itself may seem like a good level of agreement. And when you read psychology articles, you can see that researchers very frequently report measurements of their agreement or measurements of how well there was a consensus between the two researchers, and that gives us more confidence in the results, especially if we want to draw important conclusions from them. So in this example, reliability was calculated between 2 independent raters who were scoring interview transcripts of interviews conducted with children. And these researchers wanted to ask simple questions about how much information can children remember. And so 2 independent researchers took a random sample of 20% of those transcripts, went off independently, counted up all of the bits of information, and then they sat back down and looked at exactly all the points of agreement and disagreement that they had, and then they went on to calculate their percentage of reliability. Now, the problem is that calculating percentage agreement, although it looks on the surface to be a fairly good and objective way of measuring agreement, it doesn't quite account for some other anomalies that can creep into data collection. And so yes, there was 8 out of 10 agreements, but that calculation doesn't account for dumb luck and simple chance scores. So in theory, although there was 8 agreements, there might not have been 8 true agreements. It might be that there were fewer agreements, but then just by sheer luck or guesswork, the raters chose the same answer. And so what researchers and other statisticians have proposed is Cohens Kappa. And this accounts for those sort of chance agreements in the calculation itself. So let's take a look at the Cohens Kappa equation. And here's the equation on the right, and on the left we've got the breakdown of what the different symbols and letters mean. So K is kappa, and it is saying that Cohen's Kappa equals the sum of all of the agreements minus the expected frequencies, with all of that divided by the total number of observations minus the sum of the expected frequencies. And now that might seem a little bit confusing to begin with, but let's break it down and start taking a look at what that might mean. So let's look at our example again. We've got judgments about the effectiveness of drug A and drug B, and they have been independently made by two different researchers. We've got the first researcher and we've got the judgments of the second researcher. So we want to have a look at how we might be able to calculate Cohen's Kappa based on the equation that you've just seen. And here are my calculations, and I would encourage you all to take a bit of time and to run through some of your own calculations just to convince yourself that you understand the underlying workings and rationale of this particular equation. So what we've got here is basically a simple tally that I created in the box at the top. You can see that I have put one researcher on one side of the box. At the top we've got the ratings from the second researcher, and all I'm going to do is go through and mark exactly which decision was made by each researcher. And if you were to go through the data, you would end up with a matrix that looks a little bit like this one here, with two lines in the top left-hand corner, 4 lines in the middle, 2 scores in the bottom right, and then there are a couple here where people made different observations. Researcher 2 scored stage 2, while the second researcher only scored that as stage 1. And there's another observation here where the first researcher scored something at stage 3 when the second researcher might have just scored it as stage 2. But anyway, with those tallies we can turn those into numbers, and you can see there in the second matrix at the top I've got some numbers. Then you can go ahead and calculate row and column means with the grand number in the bottom right hand corner. And as I said, if you were to look at simply just the number of agreements divided by the total number of observations, you would get a score of 80%. But if we're to apply Cohen's Kappa here, that Kappa equals the sum of the agreements minus the sum of the expected frequencies divided by n minus the sum of the expected frequencies, we end up with these calculations here. So it's a simple case of thinking, well, what are the expected frequencies? The expected frequencies are the row and column totals multiplied together, and they are all divided by the number of observations that are being made. And if you were to work through this calculation step by step, what you would find is a Cohen's Kappa of 0.68, or in other words, 68%. So that's a different type of statistic that we're getting from using Cohen's Kappa compared to percentage agreement. The percentage agreement's 80%, but Cohen's Kappa is only saying that we're 68% reliable. So that is interesting. Cohen's Kappa is therefore a little bit more conservative, and even with good overall agreement, you can still end up with a little bit of a lower Cohen's Kappa score. You can calculate Cohen's Kappa in SPSS. In the menus, you will find options for conducting chi-squares and Cohen's Kappa. You would arrange your data into a couple of columns. You would just select those columns in the menus, indicate that you would like Cohen's Kappa calculated, and then have SPSS run it. And then when SPSS runs that calculation, it is using exactly the same formula in exactly the same way that I went over with you in the previous slide. And just to confirm our own calculations, when we run that through SPSS, you can see here in the bottom table, we have a kappa value of 0.68, which is what we calculated ourselves too. So that just confirms that we have an understanding of how those numbers in SPSS might have been produced. Now there are some advantages to working through the equation a few more times just to satisfy yourself that you're understanding the ins and outs of Cohen's Kappa and why it is a little bit different from relying simply on the percentage of agreement. So what I've done here in this slide is created a couple of small matrices with easy numbers, and I've gone through and calculated both the percentage agreement and the percentage of and Cohen's Kappa for these different matrices where I've just been interested in fiddling around with the numbers a bit to see if it makes a difference. So in this first example here at the top, what I've done is got this 2 by 2 matrix, and I've just put 2, 2, 2, 2 in each of these squares. Now, if we were to look at the percentage of agreement, what you would find is that these researchers, researcher A and researcher B, making judgments X and Y, agreed on XX twice, they agreed on YY twice, and there was a total of 8 observations. So if you were to look at percentage agreement, that would mean that you have 50% agreement. Well, is that good? If we go through and calculate Cohen's Kappa using the formula and using those numbers in the top matrix, we end up with a Cohen's Kappa of 0. So while we might have inter-rater reliability of 50%, Cohen's Kappa is saying 50% is not good enough at all. And in fact, if you're going to agree as much as you're going to disagree, we're going to give you a Cohen's Kappa score of 0, because the calculation and the idea behind Cohen's Kappa is to give a strong indication in situations like that you have a very unreliable way of making your observations. So in the next one here, I've just thrown a couple of observations, out. Most of them are agreeing, so we've got 3 XX agreements, we've got 3 YY agreements, and then we've got a disagreement where the researchers have both made different judgments. One's called it Y when the other has called it X, and vice versa. Now if we were to go through here and look at the agreements, we've got 3 XX agreements, we've got 3 YY agreements. It's a total of 6. 6 divided by 8 is 75%. So if we were to use a simple measure of percentage agreement, the agreement's better at 75%. But what does Cohen's Kappa say? We go through the calculation, making the careful transpositions of the numbers between each step. And Cohen's Kappa produces a value of 0.5, or in other words, 50%. So it is an improvement, and it's saying that we're 50% reliable, but it's not giving us a lot of credit. And it's certainly not giving us as much credit as simply looking at percentage agreement, which was 75%. Now, if we look at the bottom matrix, there's the same number of observations, there's the same number of agreements, but this time I've just put both of the agreements into the same category. So researcher A has chosen X and B has chosen Y, but they've both done that. So that's a type of error, but it's a reliable error. And in science, if we find errors, if they have a pattern to them, then it gives us something that we're able to fix. We might be able to ask people to sit down and talk about why they see things consistently different from each other and whether or not there is something that can be done to resolve that. So as in the previous example, because we've got 6 agreements, the percentage of agreement comes out the same, 75%. But what does Cohen's Kappa tell us? When we go through the equation here and solve K and produce our next Cohen's Kappa statistic, it comes out at 0.53 or 53%. Now that's an increase from the previous calculation that we did, even though there are the same number of disagreements. So it's almost like Cohen's Kappa likes the consistency of the error, and it's prepared in the calculation to give a slightly higher statistic. And just this final example, I've increased the reliability once again. We have 7 agreements divided by 8 observations in total, gives us a percentage of agreement of 87%. And when we solve kappa, we end up with a kappa of 0.75. And so what you can notice when you're looking at the difference between percentages of agreement and the kappa statistic is that the kappa is in every case giving us a more conservative percentage of agreement. It's saying, yeah, you might be good and you might have lots of agreement, but we're still going to account for the risk factors and chance that might have occurred. So you can see some subtleties if you work through these differences here. Sometimes we have the same numbers, but we get different kappas depending on the distribution of the scores. If we have 50% agreement, Cohen's Kappa is going to produce a statistic of 0, saying that, look, if you're 50-50 as a piece of research or as a researcher, we're going to have to give you a score of 0 because you're completely unreliable and we shouldn't be relying upon your data. So how do we interpret the results then? Yes, the percentage of agreements does give us higher numbers and can lead us to think that we're in better agreement perhaps than we really are. The Kappa statistic is consistently lower, but even with the same numbers and the same numbers of disagreements, depending on how they're distributed, Kappa will give you a slightly different answer. So in some ways, Kappa is much more sensitive to the ins and outs of the job of creating reliability around your data. So what's a good score and what's not a good score? Well, with percentage agreement, it's generally accepted that anything over about 85% agreement would be considered good. Good reliability between raters. But for Kappa, there is a different scale. It's somewhat arbitrary, and you can find different versions of this if you Google it on the internet. But there are some suggestions about what you should consider good inter-rater reliability. So if you're getting Kappa scores between 10%, 0 and 20%, that's considered to be very, very poor inter-rater reliability. Between 21 and 40% is considered fair, right? Probably not good enough to make important scientific decisions on. But once you start getting over 60%, then you have a substantial and near perfect Cohen's Kappa. Remember, it's more difficult to get a high Kappa score. So when you do start getting scores over 60, Cohen's Kappa calculation would consider that to be evidence of pretty good inter-rater reliability.